Okay, welcome everyone. We're delighted today to have Leandro Aolita from the Quantum Research Center of the TII Institute in Abu Dhabi. So we're having very interesting discussions for a while, and we're happy that Leandro is with us in person today. We're going to have interesting future partnerships with TII. We look forward to more activities. This is only the beginning of a lot more activities to come. So we're delighted that Leandro is giving the talk on quantum algorithms. He's a world expert on this in this area, and explicitly on the topic from the NISQ era to the early fault-tolerant one. Leandro, please.
Thank you so much, Hisham, for the invitation. After so many communications and attempts to meet each other personally, thank you all for being here. It's really a pleasure for me to be here. I've been in the country for 1 year and a half, a little bit more, doing research in TII, which is more a corporate environment. And it's really wonderful for me to be back in a university environment and to see that this is here in Abu Dhabi, right? Because this is the first time that I'm here in the university, right? So yes, so I'm going to talk about quantum algorithms. This is the main activity of my division in TII. I'm going to try to, I don't know the different backgrounds, so essentially there's going to be a first part of the talk, which is going to be like a little bit more relaxed. And then in the second part, I will try to convey some technicisms of some recent results that we're doing, and let's see how it goes. But please interrupt me at any point. It really helps me to communicate better if you interrupt me at any point that you don't understand, right? So before we jump into the talk, I should also mention that I am still on leave professor in the University of Rio de Janeiro, and I have funding also from there. So I always like to thank my funding agencies in Brazil, especially the Serra Pilheira Institute. This is some sort of Brazilian equivalent of the ERC in Europe, and they were very kind to allow me to continue using the money for the part of the team that I still have in Brazil. I cannot use that money anymore for myself, but the fellowships, there are still 2 postdocs there. I've been absorbing part of the team that I had in Brazil to TII. Some of them, 2 of them are still there. So let me tell you a little bit before we get to science. Let me show you a little bit what is TII, how does it work, and what's the structure of the house. So essentially, TII is the applied research leg of the Advanced Technology Research Council, ATRC. This was essentially founded 2.5 years ago. And the idea is to have now one council, the ATRC, that kind of coordinates investments into applied research in a coherent way, so to say. And TII is the applied research leg of it, but there are other 2 sister institutions. Aspire is the one that kind of tries to hook us up with industry and tries to identify potential problems in the government agencies or industry that may be of interest for researchers in TII to in the end produce IP, intellectual property, and move the economy through innovation, right? And then there is a third institution, which is Venture One. This is the youngest one. They started this year, which is going to be the one responsible for one day commercialization of the ideas and methods that come out from TII, right? So Venture One will be the responsible for bringing capital to really go for incubating companies and startups. So this is this is a little bit the structure that the Advanced Technology Research Council had in mind. And this is kind of like the approach that we want to take for applied research and innovation with impact to the economy. That's it. So at the level of TII, so there are a number of goals, of main objectives. So we want to position ourselves as a hub, as a research and development hub in the region. We want to bring talent and retain talent here, and of course, to also have an Emirati component of talent. This is also important. And essentially, yeah, like I was saying, to create partnerships with different institutions, industry, government, and also other universities in the country, right? That's more or less the goals in TII. There are at the moment 10 different research centers. So I am from the Quantum Research Center, but there are other 9 research centers. And you can see this is what we were chatting. So there are different levels of maturity. Some of the centers, like advanced materials or robotics, they are closer to applications, so to say, closer to commercial impact. And then you have quantum center, which is more foundational, right? And so this is something that upper management understands, that we have a much more academical spirit in the way, because of the nature of the technology, that it's more in its infancy, so to say, right? And we're thinking big. I mean, TII is thinking very big. We're building now we work in, the labs are in a different place, but the offices are in a rented space where we only have 3,000 square meters, but we're building a campus for TII that will go to 60,000 square meters, so 20 times more. And in fact, the numbers that they manage for the future is to expand to 20 centers altogether. So this is really a very ambitious initiative from the Abu Dhabi government. And yes, one of the main things is to keep the standards of scientific excellence very, very high. So let me move now to the Quantum Research Center. So we have 6 different lines. In fact, actually, we have 3 different main technologies. Quantum computation, this is quantum hardware, quantum experiments on superconducting qubit devices. We also have quantum communications. This is about doing communication schemes and cryptographic schemes with entangled photons of light. This is like optical experiments. We also have quantum sensing with atoms. So there they trap atoms with optical tweezers, and for instance, they want to use that for sensing, for measuring with very high precision, censoring of forces and inertial sensors. And then we have 3 theoretical lines. These are the quantum algorithms division. I am the head of that division. We also have quantum middleware, which is about classical computation and all the classical computing overhead required to make a quantum computer work. And then you have quantum physics, which is the theory behind superconducting qubit devices and atomtronics and spintronics, a little bit of condensed matter theory too. So it's a mixture. It's a mixture of people that came from academia, and some of them continue doing very academical stuff. Some of them are doing more applied things, but it's a heterogeneous mixture of people. So just to give a little bit of the demographics of the center, we started 2 years ago in the middle of the pandemics. Many of us started working remotely in the beginning. We're reaching now 60 people, probably reaching 80 or 90 people by the end of next year. We have interns coming and going, staying for 6 months. We have a good female component. From these 60 people, 52 are researchers, right? Half of them already have a PhD, the other are pursuing a PhD, right? But we have, in just 2 years, we have 52 researchers working at the Quantum Research Center. So then, after this brief introduction, let me start coming closer to the topic of the talk, right, which is quantum computation. So I don't need to maybe say that this is expected to be the next leap in high performance computing, and essentially, this is a big hype, both in terms of private investment and in terms of public investment, public initiatives, because it's an emerging technology with a huge disruptive potential, right? So the idea is to use quantum properties like quantum entanglement or quantum superpositions. These are properties that happen at the level of atomic or subatomic particles, and the idea is to use these properties to process information. And this is leading to novel type of quantum algorithms that will be able to solve problems of commercial interest, of practical interest, that are today intractable even by the most powerful classical supercomputers, right? And this is why people are making such a mess, such a mess, but such a fuss with quantum computing, because it has a huge disruptive potential, right? It's still in its infancy, the technology, but hardware developing is going very fast, and investments are going very fast, right? So things are moving quickly. And so there are many, so here I kind of suggest like different type of scientific applications that you may have. So we will probably have one of the first things that we will see is quantum simulators for simulating organic molecules in chemistry or material science. We will also see impact on physics and mathematics, code breaking and linear algebra algorithms, quantum communication, what I was talking about. And of course, one of the big things, maybe quantum machine learning, using quantum circuits as a platform to run AI and machine learning algorithms. This is a big thing. And there are many things here that people are thinking about on at the level of quantum algorithms. But something that I want to make that I like to show when I give talks here in the region is like, okay, what are the main potential use cases for the region, right? So for instance, I was mentioning quantum simulations for organic molecules. This is something that big pharmaceutical companies in the world are looking at. But here in the UAE, we don't have a huge pharmaceutical industry, but we do have an industry. So we have industrial and commercial applications for cybersecurity. Of course, we have Abu Dhabi and Dubai as big financial hubs. We're in a region that's interested that, of course, oil, gas, and energy is a big thing, especially now with sustainability as one of the key priorities for the country. And of course, logistics, transportation, aviation. So there are a number of so here, like these four main lines is like the easy to digest names. Everybody knows more or less what finance, what's oil and gas. Maybe you have this in bullet points. There are the more technical topics that we tackle, right? So optimizations is one big thing for which will be benefited from quantum algorithms, and this can be applied not only to portfolio optimization but also to optimize automatize production lines or schedule flights, logistical routing, warehouse optimization, and traffic control. You know, these are things that look at different things, but if you look at the algorithmic engine that sustain those applications, it's essentially algorithms for solving something called combinatorial optimization problems. And these problems will be a type of problems that will have a speed up, a computational speed up when we have large enough quantum computers, right? I mentioned quantum simulations. I mentioned simulating molecules, but these algorithms can also be applied for simulating materials, and these may have an implication on solar cells and catalysts and batteries. Also computational fluid dynamics and partial differential equations. This is something that will be benefit. This is interesting because I was when I come a little bit to what we do, you will see that there are different ways to tackle these problems. And in fact, we are now establishing a collaboration with INEC, the Emirates Nuclear Energy Company, to understand the computational fluid dynamics and neutron transport problems inside a nuclear reactor, right? So again, this is doing forefront. We try to do forefront research at the algorithmic side, and somehow step on top of industrial collaborations to start moving towards applications, right? What else? Monte Carlo simulations. So you may see here derivatives pricing or risk management. The algorithmic engine behind this is Monte Carlo estimations, the same type of Monte Carlo estimations that we use for statistical physics, so to say, right? And so quantum algorithms will be able to offer a speed up also in computational runtime for Monte Carlo estimations. And this has a huge number of applications. Here I mentioned financial applications because this is something that is strong here in the country, but in the end of the day, what quantum computer will be able to solve, to do in a faster way is Monte Carlo estimations with the same statistical error at a much shorter runtime, computational runtime. So this is just a big kind of panorama of potential use cases of quantum computation, and in particular quantum algorithms that may be relevant for the country. Then, of course, this sounds great, and this will be a disruptive technology, but there is a catch here, right? So many of the applications that I showed will require something called quantum error correction. So I mentioned that due to, the whole idea behind quantum computing is to exploit quantum properties as the superposition principle and quantum entanglement to process information. But these properties, as you may know, they are very, very fragile. So if you put qubits in contact with noise or some thermal bath, so typically this is subject to noise and the detrimental action of interactions with the environment. This kills your quantum properties. These quantum properties are very, very fragile, and the qubits very quickly turn into classical bits, and then you lose any potential speed up with respect to classical computation, right? So the way that people have envisioned to deal with that is something called quantum error correction. But the point is that quantum error correction requires a large number of extra bits to encode quantum information. So if I have an ideal qubit, perfect, without noise, well, I need, 286 qubits to simulate a molecule of penicillin, the first antibiotics that was discovered, right? But if I now take into account noise, I need to do quantum error correction, and this is very hard. And it happens that the noisier the qubit is, the larger the number of extra qubits, physical qubits, that I will need to encode one logical qubit. And then something that you thought that was going to take you 300 qubits may end up take you 30,000 qubits, or 1 million qubits if you want to factor large numbers using Shor's algorithm. So depending on the type of algorithms that you want to solve, and depending on the connectivity and the error rates of the physical qubits, you get a number of logical qubits with some logical noise level, and then you see what you can do with that, right? So, but I mean, it's fair to say that if we really want to go for advanced applications, we're still far away from there, precisely because of this issue, right? So this leads me to what we are actually trying to do at the Quantum Research Center, and in particular in the Quantum Algorithms Division, is we want to bridge the gap from the algorithmic side. So that's from the theory side. So we have these beautiful abstract quantum circuits and Bloch sphere, hyperspheres with states live. And then in practice, we have machines, prototype quantum computers, and we're trying to bridge this gap. So from the algorithmic side, we have mathematicians and computer scientists, and of course, theoretical physicists, and we're trying to simplify the algorithms, make them more efficient, try to see in which way we can simplify them in order to make them closer to the prototype machines that we have. And on the other hand, we have experimental physicists and engineers trying to improve the hardware also, right? So I'm mostly going to focus now from now on the algorithmic side of the story, because this is what I do, okay? But so I should mention also that these pictures were taken in Master City, in our lab in Abu Dhabi. Over there, you can see the fridge, the refrigerator that creates. So this is the most expensive part of the experiment, but actually this is just for cooling down the system to a temperature that is colder than outer space. And the actual experiment takes place inside a cavity, a golden cavity. You may not see it there, but it's written qubit number 1, 21st of September 2022. This was the first qubit manufactured in the Arab world, right? And it was done in our lab in Master City, and essentially, so there you can see the lithography images. So this is called a Josephson junction, and this is the main, let's say, platform that divides our superconducting qubit. I'm not going to enter into experimental details, first of all, because I wouldn't be able to transmit you all the details, but also it would require us an entire separate session for this, right? But I just wanted to mention that these pictures were taken here in Abu Dhabi. So essentially, okay, I said that we want to bridge the gap from the algorithmic side between quantum abstract software and actual and quantum hardware that we have, right? And how we do that? Okay, now I am zooming in a little bit more on our activity. So we have like 3 main research lines within the Quantum Algorithms Division. One of them is quantum algorithms, quantum enhanced algorithms, I call them. There are some algorithms that use something that is run on quantum hardware. Another thing is characterization and benchmarking of quantum devices. And the third thing is something called quantum-inspired algorithms, which I will explain in a minute. But let me first tell you what I mean by this axis there, the y-axis. So by NISQ devices, so this NISQ, the abbreviation NISQ, means noisy intermediate scale quantum devices. This is, and people call it the NISQ era. We are now in the NISQ era. We are now in the era of devices, quantum platforms that may at most have 100-ish qubits, a couple of hundreds, maybe 200 qubits, with relatively high error rates yet. So it's not much you can do there. So it's still an open question. So there have been demonstrations. You may have heard of quantum supremacy experiment by the Google team. There have been demonstrations of mathematical tasks that people have solved with NISQ devices that can solve a mathematical problem faster than any classical supercomputer can do. But this task has no application, no practical application known yet. So it's still to be seen whether there will be some useful demonstration of a quantum advantage in the NISQ era, or maybe transitioning towards the early fault-tolerant era. So for running advanced algorithms like Shor's factoring algorithm for decomposing a number into prime factors, we will need full-fledged quantum error-corrected platforms. This is what we call full fault-tolerant quantum computers, right? Advanced algorithms will require that platform, and we still don't have that platform. There will be something. There will be like something in between, which people call early fault-tolerant era, which incorporates some sort of error correction primitive, but it's still not fully fault-tolerant, right? And so essentially, we are tackling the whole spectrum of applications there. Of course, we're interested a lot in NISQ and early fault-tolerant, but there is part of my team working also on advanced algorithms, also again, the idea is to try to simplify and make all these algorithms more efficient, right? And then you may see names like some of them I mentioned already: quantum simulations, variational quantum algorithms. This is a big thing if you want to do machine learning. So essentially, in machine learning, what you do, you train a neural network. You do it in some variational way. You have some ansatz, and you train a neural network. Well, how about using quantum circuits as your neural network? This can be done. So this is what people call variational quantum algorithms. There are many things that people are looking at. Then we have high-dimensional linear algebra, quantum machine learning, and again, combinatorial optimizations, factoring things, advanced algorithms that I was mentioning. On the side of characterization and benchmarking, this is something that is mostly like kind of like an internal debugging thing for the quantum community. This is not something that we are going to sell as final product of quantum computing. This is something that we need to make sure that the quantum machines that we're building work in the proper way, which is not a minor thing. Because, so, quantum computers will work in a different way. And so one day in the future, when we will have a big quantum computer able to factor large numbers, then great, I give you a big number. And if you tell me you have a quantum computer, I give you the big number, and then you manage to factor it. And then factoring is a problem that is difficult to solve, but easy to check if you give me a candidate solution. So then it's easy to check, to have trust that the computer is working in a good way. But we're still not there. We're still in much more primitive machines. And so how to certify, how to benchmark, how to characterize the noise in a quantum machine requires really like conceptually new ideas. And this is an entire research line within the quantum algorithms team. There are very smart people coming out with very sophisticated mathematical methods involving randomized measurements and group theory to try to exploit and learn the most out of a quantum system in as few measurements as possible, for instance. This is a big thing. We need that for, we need to understand the noise of the system to be able to then calibrate quantum chips, or to be able to do error mitigation of quantum chips. Error mitigation is some sort of light version of quantum error correction. And so in order to do these things, you need to have a good characterization of your system. And this is very, very hard. Yes, please.
Sorry to interrupt. So one question. So are you building some noise models based on this thing, like whatever studies you get with the physical machine?
Sure. Yeah.
So okay. So I mean, since I did a lot of fault-tolerant computing for the traditional CMOS design, we get the manufacturing defects and things like this. So I can already envision that if we are given a certain noise model, we can redesign the algorithms, or at least the circuits, such that they are more robust in nature.
Yes.
For this thing.
Yeah, that makes total sense. And there are even already there are startups, quantum algorithms doing those things. Like, yeah, you're right. I mean, how to best design a quantum circuit changes if you know the type of model that the platform suffers, right? And so, yeah, this is totally the case. And so we imagine here, this type of benchmarking and characterization, where we have to do it for our own quantum hardware. But also in the future, if we think big, we imagine like some sort of calibration and characterization facilities here in Abu Dhabi, where people, so for instance, we are in the lab, so we are going ahead with printing our own chips and manufacturing our own chips, but we're also establishing collaborations and partnerships with startups or different centers that give us their chips. And so some startups on quantum computing, they are already selling chips and they're not really very well characterized. So it's this thing of benchmarking and characterization is something that doesn't come out to the outer world, because it's not this that has directly an application in industry, but without this, the field cannot progress. And yes, there's definitely lots of room, especially on this thing of noise mitigation. Yeah, this is a big thing.
And we can actually incorporate this noise during the let's say machine learning model training.
Sorry, say it again.
So let's suppose if I'm training a QML model that I have, I can actually incorporate that noise model in order to even retrain the network, which is more robust to this noise.
Exactly. Yeah. That's true. So the other thing that people okay, and then there's this third line here, which is this quantum inspired methods. This is something interesting that's happening nowadays. So so these are classical algorithms. These are and therefore, of course, they can be deployed in current nowadays classical hardware, and somehow these methods, essentially what they do is they take some inspiration from quantum approaches. You see, like doing research on quantum algorithms is not just about developing a new language, programming language. It's really like thinking of computational problems from a totally different algorithmic perspective. And by doing so, sometimes you get ideas that lead you to new classical algorithms, to like different ways of solving the same problem, still with classical hardware, but giving you different approaches that sometimes people are observing also speed ups there. So for instance, there are very sophisticated techniques. So for instance, it's called tensor networks. These are very sophisticated techniques that have been partially motivated by the classical simulation of quantum circuits. And these techniques, they can handle very high dimensional vector spaces and do crazy things there. And they are very sophisticated, and people have applied them to simulating classical circuits. But there are other situations that involve very high dimensional vector spaces that you can do with that. So for instance, I mentioned here partial differential equations, computational fluid dynamics. Again, we find Monte Carlo simulations, and Fourier transforms. So you know, there are lots of algorithms that use the fast Fourier transform. So there are things also that you can speed up the level of quantum-inspired methods there. So this is something kind of new, and it's taking lots of momentum within the field because, you know, not only are quantum algorithms like an intermediate step towards the final goal, towards the ultimate goal of quantum algorithms, but they also offer some interesting speedups today, right? So this is also an active research line within the quantum algorithms division. And this is kind of like the big picture panorama, right? And I'm doing quite well, so half the talk, so half the 20 minutes. So let me try to get more technical now, okay, to give you like example of some of the things that we're doing, right? So let me finally talk some serious science. So essentially, what I will try to convey in the last half of the talk is two recent works that we did. So the first one is something called quantum interfaces to give circuit boosts. This is kind of connected to error mitigation and what to do with these NISQ devices. What can we do with these NISQ devices? Can we push? How far can we push these NISQ devices? Then I would like to say something about a little bit more advanced, to relevant maybe for the early fault-tolerant era, to convey a little bit, because I'd really like to show you how one thinks when one goes really quantum, right? So hopefully I'll manage if time allows. Essentially, let me start then by this NISQ Era applications, and one good starting point is a paper that we wrote in collaboration with people in Canada, in Vector Institute, Juan Carrasquilla especially, and Roger Merkel in the Perimeter Institute. Giacomo is nowadays in Amazon Web Service, and they have a quantum center now in Pasadena in collaboration with Caltech. And essentially, back there, what we did was to apply, let's say, classical neural network techniques to characterize a quantum state. So this is again within the realm of characterization. So and let me tell you why this connects with the quantum interfaces that I would like to introduce today. So essentially, back there, what we did is the following thing. Imagine that you have a quantum state. You know, this can be a quantum computer with many qubits, and then I ask you, okay, tell me what's the state of this quantum computer. So if it's a noisy system, you know, the full description of the system requires that you tell me the density matrix that describes this state, right? That's the full characterization. And so essentially what we developed there is a technique such that you go to the lab and you make local random measurements in each qubit, right? So you have n qubits, and you can imagine that you can choose in which direction to make a measurement. You can measure, you know, I will become more technical. Please stop me when you don't understand any, or if I'm saying anything. But essentially, a measurement can be described by a random choice whether to measure X, Y, or Z, where X, Y, or Z are the Pauli matrices essentially. And so essentially, so this method that we developed there. So you go to the lab and you just randomly choose whether to measure X, Y, or Z in each qubit, right? And then you get some statistics out of there. And from these statistics, you try to build a neural network, a classical neural network that learns this probability distribution. So this connects to something called generative modeling, which is a big thing in unsupervised learning and machine learning in general. Essentially, generative modeling is I give you data, I give you random data, and now I ask you to build me a probability distribution such that if I put in a black box and press a button, it will give me samples that will have a statistics as close as possible as the sample statistics, the training data that I gave you. So these were very sophisticated techniques that were advanced already at the level of big data, and so we applied it for the application of reconstructing the density matrix of the state. And so the way it works is essentially the following one. So there is something, I don't know, there is this, anyway. So there is this, so here, what I'm representing is something called a factorable informationally complete measurement. This is what I was saying. So an informationally complete measurement is if I randomly measure X, Y, or Z, and I repeat that, this will give me statistics that will be informationally complete in the sense that if I gather enough statistics, I am able to reconstruct exactly the density matrix of the system in which I'm measuring. And
don't you need also the identity together with the X, Y, and Z? Because altogether they form basis for 2x2 matrices.
Great question. The answer is no, but the question is still great. So it's true that if you want to go for let's say the entire decomposition of any density matrix in terms of Pauli matrices, you need all the 4 to the n different Pauli strings that you got. But the identity is special because density matrices have trace 1, and so just by normalization, you know this is the one the one Pauli expectation value that you know what's the value that's going to be, right?
It's of the normalized identity, like when you have trace 1, when you make it trace 1. 1/2, like 0, 0.
So I mean, if you trust that you're not losing particles and you're not losing clicks of your detectors, you don't even need to measure that. But also, since we're using machine learning, so what we did back there is to we have like an ansatz for this probability distribution based on some classical neural network, and we can already impose trace 1 there at the level. But yeah, so it's not needed to measure that, and also locally, you see. Even if I want to do it, I still can do it, because measuring say that you want to measure the expectation value of Pauli X. This means that you prepare a measurement such that sometimes you get click on plus, sometimes you get click on minus, and then you process that to calculate the expectation value of Pauli X. But these same statistics can be used to get the expectation value of the identity. You see, the expectation value of X is probability of getting plus minus probability of getting minus. And then the expectation value of the identity is probability of getting plus plus the probability of getting minus. So from the same observed probability, you can already calculate that for free. But that's a great question. Thanks. And so what we did back there was so the reason why I start here is because the representation of the states that we use for there, since there we wanted to learn the state by learning its probability of outcomes. So there is something that you can do, which is express. So again, if you imagine like random measurements on each qubit, so they're factorable in the sense that they are not correlated between each qubit. So it happens that this this kind of operator MB there, this is not the Pauli's operators themselves. You could do that because they're a basis, like you mentioned. But in our case, there's something more general. Like you could have like random, you could project onto eigenstates of Pauli's in random directions, for instance, something like that. So there are all type of crazy things that you can think of, informationally complete measurements that go beyond just the Pauli's or simple von Neumann measurements. The important take-home message here is that any density matrix can be expressed as a linear combination between your measurement operators MB and your probability distributions of outcomes. And there is some sort of inverse overlap matrix there that kind of mediates between the probability and the measurement operators, which is given by the inverse of this overlap matrix. So this tensor TAB is like the trace of your measurement operator. So this before the experiment starts. And so what I'm telling you is that if you are able to characterize precisely to reconstruct the full probability distribution, then I can, in principle, write down the density matrix using this formula. So the entire experiment with machine learning there was like, okay, let's learn the probability distribution with classical generative modeling. So that was the first paper. But in the end of the day, the important thing that we use here is just the representation of the state. So here, it's interesting because I'm telling you that any state can be represented as a linear combination of factorable operators. You may tell me, how do you manage to represent an entangled state there if it's factorable? But the thing is that this tensor t to the -1 has also minus signs. And this allows you, so instead of having like a convex combination, so you have an affine combination, and you can represent all states with these guys, right? So it happens that, so the application that I'm trying to go for now is to use the same type of representation, but to create like a window of classical simulation inside a quantum circuit. And this is actually these quantum interfaces that I wanted to show today. So yes, please.
The previous representation for rho using the T inverse, this is an exact representation for it.
Yes.
And now.
Yes, and it's not unique. That's the reason why now I have a tau, which is there is some freedom there. Like even if you fix the choice of measurements, if the measurements are a frame, so the technical work is a frame instead of an orthogonal basis, the choice of the tensor that connects. So in other words, this tau, there is some freedom of gauge in the choice of this tau there, but that's a little bit more technical. But what I want to say is that, yeah, so imagine that, yeah, if you believe me that I can express any density matrix like that, then I can do the following thing. So if tau was, so tau is not a stochastic matrix. Imagine that tau was a stochastic matrix. So then we could interpret it as probability of B given A. If that was the case, then that would kind of be like an average, you know, like we have probability of A that depends on rho, and if tau of A and B was the probability of B given A, then this would be like an entire, the expected value of the MBs, because you have probability of A times probability of B given A. This gives you probability of A comma B, and then this is an average, right? And so we could simply go to some experiment or some technique that kind of samples A and B and produces statistics of A and B, and then I average just the MBs according to that. This is not the case because this tau is not a stochastic matrix, it has negative signs. But what we can do is to absorb the signs, and that's why I have now the sign of tau of A and B, and then to divide and multiply by the one norm of that matrix. And so this is what I call the negativity, which is this norm one of this tau, and essentially come out with a new distribution, which is this P of I, such that, you know, I go to the lab, I make these measurements, and I get A, and then now I sample B from this distribution. And then essentially, this gives me like a collection of A and Bs, and then I can evaluate that thing over there. That thing over there is, again, so the sigma Bs are the same MBs that I had. It's just that now I normalize them to make them be states. That's why I have this TB. This TB is nothing but the trace of the MBs. But the important thing are the signs there. So essentially, what I'm doing is kind of like I have this matrix tau. I absorb its signs and I put them in evidence. And then I multiply or divide by something that allows me to come up with a well-defined probability distribution from which I can get samples. And then if I do that, then what I'm doing is very stupid. Like I have rho, I can make a measurement of rho on some basis and get A, and then kind of from this sample, from this this quasi-probability of B, and then now I go, you know, I could think of an experiment where I have the state, I measure A, and given A, I sample B, and with B, I now go to the lab and re-prepare these states sigma B, which are all product states. And then what I could do is, if I am able to then somehow, in any post-processing, in any thing that I will do for that density matrix, I am able to bring back these signs, then I'm doing nothing. I get the same state. So this is a very stupid way of kind of like a hybrid classical quantum Monte Carlo simulation of the identity map. I had the same state, and I get the same state. I measured and kind of re-prepared product states, and then somehow I need to bring back the signs. This is done by classical post-processing. But what I want to say is that this is a very stupid way of implementing the identity map. This does nothing, but the idea is now to use it for simulating some non-trivial quantum gates. And this is like the spirit of the NISQ era. So in the NISQ era, so all you want to do is, okay, try to run as much as you can classically, especially if they're simple things, and save the precious little quantum hardware that we have for the actual complex stuff. And so the application here, was that a question?
No, in fact, I was asking about what is tau A.
Sorry?
How you get tau A out of tau AB?
No, so the A, you get it as the outcome of the measurement. So you have your physical system, and now like you go and choose, so you measure these random measurements, and each measurement gives you an output. It gives you an outcome, but this is A. So you go to the lab and make a measurement, and this gives you A. Now, given A, I can come back here and see how much is the value. You know, I can fix A and now sample B given A. After doing that trick of the sign, and I need to make a conditional probability distribution appear. I will have to pay a price because this has signs, and there is something called the sign problem, and people from Monte Carlo, from quantum Monte Carlo estimations know that very well. So this will not be the solution. This will scale back eventually, but maybe for the NISQ era, we are able to contribute with some regime where this can be useful, and this is what I'm going to show. But yes, you get A. The experiment gives you A, and now me on my classical computer, I calculate, I sample B given A from that A that the experiment gave me, and with this B, I make a new experiment where I now kind of, if you want to make an experiment, if not, you just store these sigma B's in your classical computer, right? But what I'm saying is that this is some, you know, I did nothing, so there was rho, and I get something that is equal to rho, but now we will incorporate, instead of classically simulating the identity map, I will use something smarter, and I will use this trick to simulate non-trivial gates. Okay, and this is what goes in hand with this NISQ era and trying to do error mitigation. So the application that we look at here is when you have this long range, you know, quantum circuit. So essentially, so we have like a universal set of gates, and there's this CNOT gate, which is a 2-qubit entangling gate. And sometimes in circuits, you need to apply this CNOT gate to qubits that are very far apart. And then something you could do is, okay, maybe what we can, and these are very costly in quantum hardware, you need to simulate, there are limited connectivity. So typically qubits, they live on some lattice. There are some platforms now that start having all-to-all connectivity, but this is still premature. So most quantum hardware that are available, so they have like nearest neighbor interactions. And so if I have an entangling gate between two qubits that are very far apart, I need to synthesize that with a ladder of swap gates. And each swap gate comes synthesized itself by 3 CNOTs. So it's very expensive. Each CNOT introduces noise. And so applying a single long-range entangling gate may kill the entire fidelity budget that you have in your premature quantum hardware, right? So essentially what we do there is a scheme where, you know, you have a circuit and you choose some long-range gate that you want to synthesize classically. The rest of the circuit you do quantumly. But at some point when you have like a very long-range gate, so what you do is you make measurements on only these 2 qubits, you get your outcomes A, and now you do this thing that I was saying. Now we sample B given A. And then what we do is to kind of, this leads us to like kind of re-prepare states in a product state, but only on these 2 qubits, and then the circuit goes on quantumly. So in each experimental run, we store who was the A and who was the B that we got, because this will give some signs that we will have to introduce by hand in the end of the estimation by classical post-processing. So this does not simulate the quantum state by itself. This simulates expectation values on the quantum state if I bring back the signs that I threw away, so to say. So I know that this is a bit technical. We can discuss more. I'm happy just if I manage to convince you that there is a way to do random measurements on just 2 qubits that are very far apart, and then re-preparations of these 2 qubits in random states that are the same 2 qubits. I only touch these 2 qubits, and then I store the signs. I stored what was the statistics that was run in each experiment. And in the end of the day, I repeat that many times, and I will, so, you know, the experiment will give me some expectation values of the observable that I was interested in, but I will have to correct it with my signs. And this is something that I do offline as classical post-processing, right? And essentially, that's the kind of experiment that you have. So you go there and you say, I want to implement this circuit. Okay, then let's select the two gates that are furthest apart, and then use these interfaces for just these 2 gates. The reason why I do that is because you pay a price. This is not for free. When you use these quantum Monte Carlo methods, there is this sign problem, which is very malevolous and very infamous, so to say. And so essentially these schemes exploits in terms of statistics. So the more uses that I do of these interfaces, the higher the number of experimental runs that I will have to get. So the statistical fluctuations start growing. So I pay a price. This is a sign problem. And so this scales very bad. So you cannot use this trick too often in a circuit because the statistic scales exponentially with the number of uses. But the nice thing is that it does not depend. The statistical blowout does not depend on the distance between the two qubits. So this means that if you have a circuit where you have a few gates between two qubits very far apart, then you can invoke this type of tricks. And this will allow you to, if there was one single gate that required lots of CNOTs, well, we remove that. We bring statistical noise, but we kill the systematic errors. The systematic noise, the systematic errors coming from the experimental noise. And let me show you some numerical experiments, right? So, for instance, this is a simulation of okay. So we run several simulations. This is one of the ones I like the most. So essentially, this is a 20 qubit circuit. And what we want to do here is to apply a circuit that will take us to the ground state of the transverse field Ising model with boundary condition, with periodic boundary conditions. So this is a very simple model. And in fact, so people, this variational quantum circuits, that's one of the things that you can try. You can propose like some ansatz of quantum circuit and then try to prepare the ground state of some model. And people, in the case of the transverse field Ising model, people know exactly the type of circuit that has to be done for this. So this is exact. So if I make 8 layers of this circuit, I prepare the ground state exactly, right? But here, what I'm trying to say is that, so here we did a simple application where you just apply 2 layers of this architecture, and you will notice that each layer involves one very long ZZ gate. This is an entangling gate between two qubits that are far apart. All the others are nearest neighbor gates, which reflects the fact that we're in a closed boundary condition, right? So this is still kind of like academic problem, right? But this is a very explicit example where this type of trick helps you a lot, because there is only one entangling gate that is between qubits that are very far apart, and all the others are nearest neighbor. So the nearest neighbor ones, we can implement them only in quantum hardware. But if we classically simulate the one gate that is between qubit 1 and qubit 20, then you save 69 CNOTs, right? Which is kind of like 2/3 of all the CNOTs required for the layer, right? And so you can see here, like, so by doing these tricks, and again, so how much you reduce depends on how much statistics you're willing to pay, right? But here, so we show an example where we have like a 28% reduction of the errors, right?
So this is an Ising model where the next neighbor interaction is done by the Z polymatrices.
Sorry?
This is an Ising model where the next neighbor interaction is done via the Z polymatrices.
Because you have yes, the interactions, yes. There's also transverse field. There's the X terms, right?
Yes. Then what is the Rx or?
Sorry?
What is the Rx under gamma 1?
No, it's just because these things have angles. So you fix there. So this comes from variational quantum circuits. So essentially, what you check there. So this rotation X is in an angle gamma 1.
Oh, okay.
And then people started looking at they trained that in the beginning to solve for the ground state of that model. But there is an exact, so people know what are the values of beta 1, gamma 1 that give you the exact ground state if you repeat these layers for 8 such layers.
Yeah, so without this Rx, the ground state is maybe when all of them are either spinning down or spinning up. Is that right?
Sure, yes.
But with this Rx, then something else will happen?
Yes.
I see.
Which you need.
But it's still...
Because it's transverse field Ising model, it's not the Ising model itself, right? Yeah. I mean, depending on which regime you are.
Yeah, but even with that, there is an algorithm or a sequence of gates that are producing at the end the ground state. And
right.
It's known, right?
This is known because this is a very well-known model, right? But essentially, what we are able to write the ground state in terms of the quantum circuit. So this is the quantum circuit that prepares the ground state exactly. Yeah. So all I wanted to say is that this type of application, you see, this application is ideal for this type of method, because this is what I was saying of, okay, if you're in a situation where you have a few very difficult, very experimentally difficult gates, you can simply remove them. You can simply cut them out, and we can make random measurements and repreparations and simulate them classically by post-processing.
Can I ask one thing?
Sure.
In the diagram on the right, it seems you're saying you get this 28% error reduction, but at the cost of, is that right, of 10 to the 5 runs of the entire circuit? Is that what it says?
Yes.
So So that overhead is not too
Yes.
much to, I mean, that you're saying there's still an advantage here? It seems like a whole lot, like running the whole
So
circle.
10 to the 5 brands is not so much.
Okay, I see.
But you are right that this is a huge because so this is what I mentioned here. So the squared negativity. So I mean, what we need to optimize is the negativity of that tensor tau that we had, and this can be further optimized. These are still kind of they are still subject to further optimization. But this is the sign problem that kills you, right? And this is something that people, so if you look at the roadmap of IBM, for instance, that's what they want to do. They call it circuit knitting. Essentially, you want to build like several quantum chips where you simulate parts of a big quantum circuit and then post-process that classically. So this is connected to this type of works. And essentially, you have a blow-up of statistical, as we call it sample complexity, the statistical complexity, the number of repetitions row. But you have to compare what is best, right? So if you have to implement 69 CNOTs for just synthesizing one such thing, then you have to compare, okay, what is the gain that I have if because what happens is that, either you increase your number of repetitions or you stay with the same statistical budget, but then you will have a larger statistical deviation, right? And then you have to compare what's best, this statistical deviation or the error that comes from the 69 CNOTs. So, like I said, this is not the solution of the problem. This falls within this thing of error mitigation. This error mitigation is not the solution. This is not quantum error correction, but this may allow you to explore some regimes in where you can expand a NISQ device to something a bit more powerful. If you're able to trade circuit complexity by sample complexity. But yes, you pay a price, the same problem, but this is still not the last word here because we believe that this can be further optimized. We just published now this in physical review research, but there is still work to be done at the level of what are the choice of measurements that you do. This tensor tau that I was looking at, this is what controls the statistical complexity, and in particular, its negativity. It's a measure of amount of negativity there, and this depends on the choice of measurements that you do. But if I am allowed to go for a few more minutes, I would like to show you something. So this is more like error mitigation, like NISQ devices. It still has a kind of classical flavor, but I would like to give you a little hint of what we do at the fully quantum size, if I am allowed. So yeah, I think that conclusions on part one, this I already said. Like this is, this can boost not only connectivity, also circuit depth. You pair price in statistics, but it does not depend on the inter-qubit distance, right? So let me move to this early fault-tolerant era. Let me show you something about quantum imaginary time evolution. And imaginary time evolution is not something crazy about space-time. It's simply the process of a quantum system when it cools down to ground state, so to say, right? And this has, so essentially it's about preparing, applying this type of transformation. So this is a type of transformation that you use in a quantum system if you want to prepare a Gibbs state of a given Hamiltonian. So H here is a Hamiltonian, beta is the inverse temperature, and then this is what QT, quantum imaginary time evolution, does, essentially, right? And why is this interesting to quantum computing? Well, it has a plethora of applications. So first of all, this is useful for ground state optimization. So we were talking today of quantum chemistry, right? So imagine that you want to study the properties of ground states of a molecule, right? And also optimizations. So if you go to classical optimizations, like combinatorial optimizations, they also happen if you formulate them quantumly. So you also can solve them by cooling down an Ising Hamiltonian, like the most classical quantum Hamiltonian that you can have. But also from the point of view of preparing Gibbs states of general Hamiltonian, so partition function estimation is interesting for statistical physics, quantum generative modeling, what I was talking about today, like kind of models for stochastic processes, for machine learning, all these neural networks that sample from classical Gibbs states. There's also people are also thinking of the quantum counterpart of that. Okay, let's use quantum Gibbs state to sample from classical distributions or quantum outputs also. And then it's connected to something called semi-definite program solvers. So semi-definite programming is a type of convex optimization, which is very well understood classically. And if you do it quantumly, it is predicted to have an exponential speedup in runtime there. So the main algorithmic component there of quantum SDP solvers is preparing quantum give states. So essentially, you give me a classical instance of semi-definite program. It's like a generalization of linear programming, and I can find you a quantum formulation that is based on preparing quantum give states with respect to a Hamiltonian that is given by the instance. So this is something with many applications. There's Krylov spaces. I mean, there are many methods that rely on imaginary time evolution, and people have been looking at with heuristical approaches and some kind of variational approaches, but there is a more formal way to do it. If you want to control precision, we're focused on high precision algorithms. This means that, you know, I give you a stand, I can guarantee, I can upper bound the complexity that this will take in order for you to have an approximation of the final give state up to approximation epsilon, right? That's the way like computer scientists would tackle the problem. So essentially, something that is interesting and I think is instructive to show is the notion of a block encoding. So if you go back here, you will see, okay, well, you know, this is the quitter propagator e to the minus beta h. So this is what drives the imaginary time evolution, but this is non-physical. This is, you know, if you think about it, it's a non-unitary. So if you are strict, you will say, okay, quantum systems, if you take into account all the interactions, so the evolution is given by a unitary operator. And we want to build quantum circuits that are as close as unitary gates as possible. And so the first question is, okay, then how do we simulate the quitter propagator with a quantum circuit if the quantum circuit is supposed to run unitary gates, right? And the way we do that is by something very simple, which is called block encoding. So essentially what we do is, imagine that we have a system S, and we initialize it in a certain state psi, and we want to apply the quitter propagator to it. So then what we do is, okay, then we add some ancillary system A, and now we run a big quantum circuit on the extended space of both system and ancilla. And if we do things well, then what we can do is we start our ancilla in a reference state 0, and we kind of measure the ancilla, and if we're lucky, we get the outcome 0. And if all that happens, then bang, your state on the system is projected onto the quitter propagator having acted on the initial system state. That's the idea of block encoding. If you think of the matrix representation of this big unitary, then you see that what happens is that the block corresponding to your ancillary system being in 0, 0 corresponds to the actual matrix that you want to implement, which is this quitter propagator. And then, right, okay, and there is a post-selection probability. So this process is probabilistic because I mentioned that you also need to make a measurement on the ancilla, and this happens with a certain probability that can kill your performance and again inflate your statistics, right? So this is also again a question. So you see, the fact that quantum theory is intrinsically probabilistic, it always kind of at some point this probabilistic nature manifests itself also in the complexity of these algorithms, right? And so, but this is the notion of block encoding, and this is what people in quantum algorithms have done to encode the quitter propagator into a unitary thing that you can synthesize in a quantum circuit up to good approximation, right? And so there are very, yes?
Sorry, maybe just to double check, in saying this, you kind of left implicit that you mean to run this as a repeater until its successor, right?
I will come to this point. Wait, I will come to this point.
But isn't it already implicit here? I mean, that's what you mean, right? You mean
that's what I mean. But there are smarter things that one can do. Yeah. Mm-hmm. Okay. But first, before we get to how we take into account those measurements, because here I'm telling you, okay, there is some unitary such that its blocks, its upper block is your quitter propagator. Okay, you can believe that, but how do we go and create a quantum circuit that implements this unitary? You know, unitaries are synthesized by 2-qubit entangling gates. And so how do we, maybe you tell me, okay, but maybe you need an exponentially high number of these 2-qubit gates, and then this is useless, right? And so, no, there is a very solid theory called quantum signal processing, these QSPs, like a modern framework for quantum algorithms. And essentially, so what you do is, first of all, you need to have some quantum encoding of the problem. Remember that, you know, I need to synthesize this quitter propagator, but you need to tell me for which Hamiltonian. and you need to tell me at which beta, right? All computations or algorithms have some inputs and some outputs. So here the inputs are like, okay, tell me which Hamiltonian and at which beta you want this, and then I will design a circuit that does the job. And this is something called oracle-based algorithms. So the oracle is something that kind of is like the quantum encoding of your problem instance, of your Hamiltonian in this case. And so this oracle is itself a little circuit that somehow connects and contains an encoding of the Hamiltonian. So I don't need to know the matrix representation of the Hamiltonian. You can give it to me as a black box. You know, it's like, okay, here, this is a little circuit inside of which there is this encoding. I'm not going to enter into the details of how this encoding works. I just wanted to mention that, you know, if you go more advanced in the type of algorithms, you need to start talking about oracles, how you encode your problem instances. But given, if you believe me, that we can encode into little circuits the Hamiltonian, then what people developed is a sophisticated theory called quantum signal processing, such that essentially what I have is my system S, and now I have my ancilla, and part of my ancilla is this AO and AP. Part of the ancilla AO has to do with the encoding of the oracle, and the rest AP has to do with what do I do with this oracle to make the QT propagator appear, to make the block encoding of the QT propagator. So one thing that these things do is to, for instance, transform a block encoding of a Hamiltonian into a block encoding of the QT propagator of that Hamiltonian. This is the type of things that you can do. And depending on the type of oracle that you have have a different primitive, right? So this is, again, very complex, and I don't pretend that you understand everything, but I would like you to at least convey the message that if you give me a quantum oracle for the Hamiltonian, then I can embed that into a quantum circuit that makes calls, queries to this oracle, and these are these queues, such that in the end of the day, I have the right thing that I wanted. And this is very powerful. It's a framework called quantum signal processing, and it's not just useful for QT. In fact, you can approximate any analytical function of any matrix if you want. And this is a big thing. This is a big, big thing. And today, when I said high-dimensional linear algebra problems, I was referring to this. So essentially, you know, quantum systems are very good for high-dimensional linear algebra problems because the classical representation of a quantum system is itself a high-dimensional vector space, right? And so there are many things that you can do at the level of functions of matrices in very high dimension that we can do with this formalism. And so what I wanted to tell you is that ideally you want to implement this primitive and you want to do it with as few calls to the oracle as possible. And there is also the question of what's the precision to which we do that and things like those. But I will stop here with the technicality because this is an entire PhD thesis. But I want to come back now to this repeat until success that he was asking. So, okay, imagine that like I have now, you give me a quantum oracle for the Hamiltonian, and I have now a circuit that is able to build a block encoding of the QT propagator. Okay, this is not a unitary transformation. QT propagation is something, like I said, that can only be successful with a certain probability. And so the most classical thing that one can do is to say, okay, well, I just do that. I measure the ancilla. If it goes well, I'm happy. If it goes bad, I start again. This is the probabilistic scheme, and this is repeat until success. And essentially, you have to try the number of times that is proportional to 1 over the success probability, 1 of the post-selection probability, right? And here you cannot see it with this little thing, but essentially what I have is like the runtime. The runtime is measured by the complexity of the circuit for synthesizing one primitive times the number of trials, right? So this is 1 over the success probability times the query complexity of implementing one primitive, right? There is something smarter in principle that one could do, which is something called quantum amplitude amplification. So quantum amplitude amplification is a technique to, like the name suggests, amplify amplitudes, right? So essentially, instead of kind of measuring and restarting again, I can make like this. I'm not pretending that you will understand why this works, but believe me, this works. So if you allow me for a further ancillary register, which is the A pure, it's called purification by technical reasons, but essentially now if you allow me for an extra ancilla and you allow me to repeat these unitaries and also introduce some ancillas, some integers that involve the ancilla, then I can end up with a final state that is as close as I want to my final good state that I wanted after the measurement. So instead of just making measurements and starting again, you don't measure. You kind of sequentially apply more and more and more unitaries, and of course, this requires a very deep quantum circuit, and you make just one measurement at the end, and you're in the correct subspace with a very high probability. But the thing, and this gives you a quadratic speedup. So that's why we have there. So the number of times there was 1 over the success probability, and amplitude amplification requires that you repeat this amplification engine in purple. In purple, a number of times that is 1 over the square root of the success probability. So you have a quadratic speedup with the naive classical technique. But there is a price to pay, which is, well, you need to have a very deep quantum circuit, which doesn't exist. If you do this on any quantum platform, you will get just noise, because noise accumulates and then you kill your quantum system, right? So the contribution in this work that we have, so this was Thais, she was actually my postdoc in Brazil, now she's here, and Marcio is in Barcelona, and Stefano is the head of the quantum middleware group here. So essentially what we did is like, okay, what if we somehow make like a somewhere in between these two things? So here, like, you measure after each primitive and you throw everything away and start from scratch. And in this one, you accumulate lots of depth and it's measured in the end. Maybe there's something intermediate to that. And this is what we came up with this fragmented scheme. So essentially there, what we do is, okay, now you use the following thing, right? So if, you know, what we want to implement is the exponential of the Hamiltonian with temperature, with inverse temperature beta. And so I can partition this into small fragments such that I can do e to the minus delta beta 1 times h times e to the minus delta beta 2 times h in such a way that the sum of all my delta betas give my final beta that I want to. And so what we propose here is to kind of partition the evolution, the imaginary time evolution, into smaller blocks, which require less depth, circuit depth, and we make a measurement at each end of, but let's say, you know, we make a measurement on the ancilla. If it goes well, we continue and apply the next fragment. If things go bad, we start again. But if things go well, you keep. So in the end of the day, if you are successful, so essentially you will have several trials, and some of them will stop at the first fragment, some others will survive up to the second one, some others will survive up to the third one, and only one will survive until the end, and that's where you stop. But you can see that this is already better than repeat until success. In repeat until success, you would run the entire primitive up to beta, and only then monitor what happened to the ancilla and throw everything away. So it happens that most of the times you can detect if you're in the wrong subspace before going to beta and just advancing up to delta beta 1 or delta beta 2. And so it's kind of intuitive that this can buy you some speed up, because yeah, you're wasting less circuit complexity in the end. And so this is,
sorry,
yes,
just to be clear, but this is a whole lot of repeat until success gates, right? Each of these small delta beta 1 gates is, you repeat it if you don't succeed, right?
Yes.
Okay.
Precisely. Very good question. So the total number, in fact, this is something that can be put in rigorously, and so the total number of trials is the same as in repeat until success. But in each trial, instead of having an entire quantum circuit that implements the entire evolution up to beta, you're running something, most of the times you will be running just the first fragment. So this is actually a unitary that's very close to the identity, because this delta beta 1 is typically very small. And so in the end of the day, you're not wasting circuit complexity. The statistical complexity is the same, but you're not wasting like deep circuits, right? So there are, of course, a number of assumptions here. So this is only useful if you're in a hardware that can, you know, you finish one run and you can start another run very quickly, which is what people expect to have soon. And that's why we believe that this is relevant for early fault-tolerant hardware, right? If your waiting time between one experiment and the other is very low, then this won't help you much. But if you have some, so most labs and companies are moving towards high repetition rate at least, and so there, these can make a difference.
In particular, I imagine it matters a whole lot here if your oracle requires you to uncompute or not, right? If you fail, need to repeat.
So what we call the quantum oracle is a fixed circuit. So this is fixed from the beginning, like the problem instance. So the problem instance is defined by beta and by h. So from the beginning, like we kind of work out what's the circuit that implements the oracle for h. and that's fixed. So now what we do is we make calls to that, meaning that we will have a much bigger quantum circuit where this little circuit implementing the oracle appears.
Right. So maybe I don't understand the oracle, but what I'm wondering is if you fail, if you don't measure zero, do you have to uncompute the result?
No.
You
No.
Okay. So you
No,
guarantee
the oracle is fixed. The oracle is like a black box to us, and so we simply say, okay, now implement a fragment with delta beta 2 and use the same oracle as before. This is the same black box that you had from the beginning.
So you guarantee that if you measure one, that your state psi will not have changed.
Yes, this is very high precision in the sense that you have a promise.
Okay.
I give you a promise. In fact, this doesn't enter here, but like the precision, like the depth of the circuit will depend not only on delta beta, on the let's say the total depth of the circuit will depend not only on beta and on h, on the instance, but also on the desired precision, the target precision. But the scaling with the precision is very good. It's logarithm. So if the error of the final state is epsilon, so the complexity scales as log of 1 over epsilon. So the main, let's say the dominant contributions to the complexity comes from beta and well, the intrinsic complexity of the Hamiltonian, right? Yeah, I guess I should speed up, right? Yeah, sorry.
So if you get the wrong measurement later on, is it correct that you just throw everything
away? Yeah,
okay.
Everything away. Yeah. There are some ideas. I mean, well, in principle, one could reuse that. You know, kind of like your unitary. One of its blocks. It's the one that interests you. The other block, in principle, you could kind of use that somehow and then map it back. It is conceivable that, but what we believe is that this ends up inflating your complexity more, because one thing is, we go to the lab, in theory, the lab, and then you have to come up with a circuit that implements a unitary on system and ancilla, but such that I'm only concerned about what it does to the system for when the ancilla is in 0, 0. If you're also concerned on what it does to the ancilla when it goes to 1, 1, then it's more requirements, and then this is extra circuit there. So in principle, one could design a way to take advantage also of these wrong measurements, but you would be inflating the complexity from another point. Yeah.
One more question: how you choose the small betas, the beta 1, beta 2? Is there any specific way or optimized way to?
Yes, we do. So let me. Yes, in fact, so that's a great question. So I mean, the most naive things that you can do is like, okay, I just have a guess. I have, I said I kind of have 5, 6 fragments. And then I take beta divided by 5, for instance. So that could be like the uniform scaling, but this is not the optimal one. There are ways to optimize that using classical machine learning, and this is something that you can do for small system sizes, and this is something that we have done. And it's interesting that you have some results. We see some scalings, like from 2 qubits up to 20 qubits. We can simulate everything classically and kind of optimize that with classical machine learning, and then you can trust that the scalings that we observe from 2 to 20 qubits kind of generalized to 50 or 60 or 70 qubits, where we cannot kind of optimize that classically, right? But we have some educated guesses of some schedules that can lead you to that. And in fact, maybe, okay, this is so I want to show a flavor of why this can work. So if you look at the overall complexity of the algorithm, so essentially, so this is this Q of delta L epsilon L, forget about it. Is the precision, but this is not so important because it contributes to the complexity logarithmically only. So the main contribution comes from delta beta. So the query complexity of the primitive of delta beta is proportional to beta, more or less, up to some logarithmic contribution, right? So it's proportional to the inverse temperature being implemented. And then it happens, you will have to believe me, that the overall complexity of this fragmented algorithm scales like this, where these p's are the success probability, right? So we have an initial state psi, and then a final temperature beta, and then at each fragment, we end up with a beta that you have beta 1, beta 2, beta 3, up to the final beta. And so essentially, the success probability decays very quickly with beta. And so you see that as L grows, so what happens is that the denominator gets smaller, smaller, smaller. And so what happens is that if you look at the yellow, so the yellow square is a representation of the overall query complexity that you would have with repeat until success. With repeat until success, you would kind of run the entire primitive up to beta and throw everything away every time you get a wrong measurement. And with this fragmented scheme, like, you run a very small delta beta, and with this specific form of the decays of this number of times that you run, well, you can see that the overall complexity is given by the region in blue there. So essentially what we need for this to be successful is that the success probability decays quickly, and then we adapt the schedules of our delta betas to that. And so here, like you said, so the optimal thing to do is to first have a very small delta beta. So the unitary that you're implementing is actually very close to the identity. So most of the times, and this is what you're throwing away most of the times, and so most of the times you're applying a very shallow circuit with very low circuit depth. Once you succeed there, you apply a primitive on delta beta 2, which is a little bit deeper. And then if you succeed, until you make it to the end, right? And so my final slide, this is already too technical, but so here we applied, so we prove theorems. That's why I wanted to show you this, because like I wanted also you to know that we tackle both. We do kind of like machine learning and variational things numerically, but we also prove theorems. There is a high component of computer science in our team. And so essentially what we have here is 3 different types of Hamiltonians. So weighted max cut is an Ising Hamiltonian on some random lattice, for instance, some non-regular lattice, right? And so these are combinatorial optimization problems. These are like the classical combinatorial optimization problem that we will want to solve quantumly. Well, we will do that with Ising systems. Then you may say, maybe we can do also some transverse field Ising model and in this geometry. And so this is the restricted Boltzmann machine, which is a case of generative modeling, this unsupervised learning that I was talking about for learning probability distributions, where people can go quantum in that. And one way to do that is give states of these transverse field Ising models with this geometry, or you can go with the most complex case, which is some sort of quantization of the Harrington-Kirkpatrick model, which is kind of spin glasses there. These are models that come from Nagel theory and condensed matter theory. So essentially, what I'm showing here is like the query complexity. The query complexity is the overall complexity of the algorithms. This is measured in terms of queries to the oracle, but we can come to these technicalities. But essentially, what you should compare, the blue one are the curves where you do uniform scaling. Just 5, 6, 7 fragments, and you use each fragment as beta divided by the number of fragments. That's uniform scaling. But then we have the optimized scaling, which is the orange one, which comes from like some optimization there, classical optimization, which we do. So this is, I think these are 12 qubits or 15 qubits. So this is a regime where everything can still be simulated classically on a classical computer, right? And so what I'm showing here is the orange one is the optimized schedule. And then the red one is repeat until success. And so what you see is that there is a point where the orange one always becomes better than the green one. And this is impressive. This is the impressive result here. So what I'm saying is that this fragmented scheme for imaginary time evolution is pretty good in the sense that if you go high enough in beta, it even hits a point where it becomes better in overall complexity as the one that we had with quantum amplitude amplification, with a coherent one, but with a very interesting extra appealing feature, which is that in amplitude amplification, you needed very deep quantum circuits. And here, the maximal depth of the circuit is just beta, essentially. It's given by beta, right? So this is very impressive. The only problem is that the inverse temperature at which this happens is already quite high. So of the order of 2 to the number of qubits divided by 2. So, but it had to be like this also, because cooling system to ground state is, computer scientists have already characterized the complexity class in which these things live. And so what I'm trying to say is that this technique is very good precisely for the problem instances that are the hardest. And even before that, even if you're not there, even if you're not at the crossing point, you see that even for lower betas, you're still much better than repeat until success, right? And so this is...
By which you mean better than a single repeat until success, right?
No. So the red curve takes into account repeat until success with all its repetitions. So this is what we call the overall complexity of the algorithm, right? Taking into account the circuit complexity of each run times the number of runs the statistical runs that you had. Yes. So I mean, yeah. So we believe that this is something very powerful. We are. I hope you can appreciate the beauty of this result. So I mean, this is something that we believe that this can be a contribution in the era of early fault tolerant. Again, this buys you a big advantage only when you are targeting very high beta regimes, and this is not always the case, but there are cases for which this is crucial. So technically, if you ask me, okay, why would I like to go to a beta so high? And then this connects to another thing, which is the spectral gap of the Hamiltonian. If you want to prepare the ground state, and if you want to cool it down so you have a give state of the Hamiltonian, and now you tell me, okay, how high does beta have to be in order for the give state of the Hamiltonian to give a good approximation to the ground state of the Hamiltonian? Well, the answer is connected to the spectral gap between the ground state and the first excited. And so there are many systems for which, relatively simple systems, for which the spectral gap is exponentially small in the number of qubits. And this is the type of systems that are ideal targets of this type of techniques, right?
So the system becomes ungapped at infinity.
Yes, well, the definition, right? Ungapped is that in the thermodynamic limits. Yes, true.
So for gapped systems, you cannot apply this.
No, you can. You can. I mean, the question is, where are you? I mean, you see, ideally, one would like to be in the green curve, but the green curve requires very deep quantum circuits. So since we cannot be in the green curve, maybe the orange curve is still better than the red one, even if you want to be in a beta that is not so high. So it all depends on, like, it doesn't here, like, it doesn't really depend on the let's say the thermodynamic limit, right? We're really given an instance, and then we kind of have ideally we would like, if you have some sort of estimate about the gap, then you can already choose in a better way which primitive to use, right?
And with it, what if the ground state is not unique? If we have some degeneracy, then the limit of the thermal states are going to be at the end of projection onto the ground state space.
Yes.
And
the same thing applies. Because for this type of, for instance, in this weighted max cut, so these are, in the end of the day, what you're interested in is to find an optimal configuration, not a single optimal configuration. You're interested in minimizing some cost functions. But yes, I mean, in the end of the day, you're right that these things also. So when I say the gap, one also needs to take into account the degeneracies. That's true. Yeah. But in the end of the day, there will always be some spectral gap, which will be the most important. So degeneracies enter the contribution to the beta that you need to get to have a good approximation. The contribution of the degeneracies enters logarithmically, whereas the contribution of the gap enters as 1 over the gap. So it's the most dominant contribution to the complexity of this type of algorithms. Yeah.
And sorry, one last thing. For the first two systems, the ground state is it's solvable. It's exactly solvable. We know them. We know them.
For the sorry, no, because this is look at the geometry. I mean, well, it's solvable in the sense that brute force solving. You mean yes, because it's only 15 qubits, so we can diagonalize the Hamiltonian and do whatever function of the Hamiltonian if we want to. But this is not nearest neighbor Ising. Like this is not a. This doesn't go to like a free fermionic model. There's no Jordan-Wigner here. Like this is like, yeah, this is when I say that we solved it exactly, I mean brute force diagonalization. Yeah. Okay, so let me come to an end. So this is something, one of the, again, so the reason why I wanted to show you this, I wanted to speak about block encoding, I wanted to speak about quantum signal processing. These are like modern powerful frameworks for dealing with quantum algorithms. And it's also one of the big foot in our division. And we did it here for Quitte, but actually this is an interesting research direction. So fragmentation as a generic primitive. I mentioned that quantum signal processing can be used for synthesizing any analytical function of matrices. Can one do the type of things that we did here for this specific application with fragmentation in other type of matrix functions? So this is one big research line. And again, it's always of trying to simplify to kind of and you pay a price, right? Like you simplify here, but then you have to blow up the sample complexity, the statistical complexity, right? But this is pretty much what I wanted to show you. These are the collaborators in Canada that I showed you. These are the collaborators for the second part of the talk. Tiago and Alan are still my postdocs in Brazil. This is kind of like part of the web page is still not updated. This is kind of like the group in TII here now. And then there are, of course, other collaborators that I'm not showing. I'm here just showing these collaborators for the two papers I talked about. People were asking me today about quantum error correction. We do many other things, but yeah, like this is the two things that I wanted to show you today, and hopefully we'll have many more chances of discussing. And with this, oh, yeah, we are always hiring, which is always important. But I'd like to thank you for your attention.
Yeah, thank you so much, Leandro.
Yeah, sorry for
interesting
it's
talk.
a bit
No,
long,
we
sorry.
appreciate your patience for taking so many questions. We appreciate it. Thank you so much.
No, it's me who thanks.
It's a very interesting talk. Any further questions for Leandro?
Maybe I have. Sorry
Please.
for asking.
No, please.
So maybe a question, not a question. Correct me if I'm wrong. So your idea that you start with a thermal state and you embed it in a bigger system and then do the measurement and get the output under certain conditions. Isn't it the same? Not the same, but it depends on the exact idea that tells us if we have a thermal state of a system, we can always embed that system in a bigger system so that the state of this bigger system is a pure state. Then by tracing up this extension, you go back to the thermal state.
Yes,
So
it's related. It's not exactly the same thing. What you're talking about is the theory of the coherence, and you're totally right. If you have, let's say, if you start by some, you have some local dynamics of some closed system, then the evolution is closed and therefore unitary. But now, if you want to implement any general dynamics, like completely positive maps or some dissipative dynamics, you can always think of that as a larger system undergoing a closed system evolution, right? And then you make a distinction between system and bath. So it's precisely the same thing, except for the fact that here, even the system ends up in a pure state. So, I mean, it depends on what you want to do. So here, what we do is like, so there's a system S, starts in psi, and ends up in a pure state given by that. And so the ancilla is kind of like, it's useful only for the block encoding. So it's a little, the guiding vision is the same, but the technicalities are a bit different in the sense that what you're trying to do here is kind of like, I have a system and I have my environment, but then kind of like, it's as if you were able to start the environment on a definite state and project it onto a very definite state, then the system would end up in a pure state also. And the pure state in this case is one such that is like kind of, let's say, a pure version of your give state, right? So it depends also, you know, you can also think that you could start in your system already in a mixture, and then you would end up exactly in a mixed state. But yes, your intuition is correct. I mean, essentially, it's the same type of intuition. It's just that in this case, you know, because you want to do this for doing computations, and so you need to have error guarantees. And the way people have come up with these error guarantees is like, okay, like I prepare my ancilla like this, I make a post-selection. If the measurement is correct, then I can guarantee you that the system state will be up to controllable precision in the kind of pure state that corresponds to quitted propagation. But yes, if the initial state of the system is also the maximally mixed, for instance, then the final state will be precisely the thermal give state. But yes, you are totally right. The intuition is the same. The intuition is the same. It's just that it's different model, and people have looked at that also as a mode of computation. So there is something called dissipative quantum computing, where instead of applying circuits and gates, like now you think, okay, well, let me now have an environment, and now if I do Hamiltonian engineering between the environment and the system, and I just let dissipative dynamics run, and then the dynamics itself, the natural dynamics itself, will lead me to a final state, which is the state that I wanted to prepare. People have looked at that. It just happens that it turns out to be not so easy because, yeah, okay, you need to control the Hamiltonian interactions in the system and the environment also. And then, in the end of the day, it boils down to you having, again, a bunch of qubits, and you make this artificial partition of which I call system and which I call environment, but in the end of the day, you need to control it, right? So there are different approaches, and it depends on whether you want to have something high precision or not. If you really want to have high precision applications, for instance, for quantum SDP solvers or computation or quantum combinatorial optimization solvers, then you would like to have like a runtime promise that depends on the target precision that you want. And then it looks like programmable quantum circuits are still the main candidates for that. Thank you.
Great. Any other questions, Leandro? Okay, thank you so much, Leandro, for presenting this talk. Thank you, everyone. I think for the postdoc, we wanted to have introductions earlier. If you like,
Sure.
we can have them now.
Yeah, that would be great. Yeah. We moved somewhere else, or we do it here?
No, we'll do it here. I just
Great.
want to make
Yeah.
sure that the system here is